Are you ready for a heart-stopping tale of space exploration? Strap in and get ready to experience the dramatic story of how NASA almost lost a $169 million spacecraft. In this thrilling video, you'll learn about the incredible technology and cutting-edge science behind this incredible mission, and the moments when everything almost went wrong. So before we start, hit the subscribe button and turn on the notification bell to stay with us on an unforgettable journey through the cosmos. Have you heard about the latest tech miracle pulled off by NASA engineers? It's a classic move straight out of the It Support Handbook, power cycling the malfunctioning Interstellar Boundary Explorer or IBEX spacecraft to bring it back to life. The spacecraft was in contingency mode, with its flight computer refusing to respond to any commands. But it seems like the solution to fix the almost 15-year-old IBEX was simpler than anyone could have imagined, just turning it off and on again. Now you might be wondering, what's the big deal with the IBEX spacecraft, and why is it so critical for NASA's mission? Well, it's not your ordinary spacecraft, that's for sure. This high-tech piece of equipment is on a special mission to study the boundary between our solar system and interstellar space. The Interstellar Boundary Explorer is a spacecraft launched by NASA in 2008. Its mission is to study the boundary between the solar system and interstellar space, specifically the region where the solar wind collides with the interstellar medium. The spacecraft is about the size of a card table, and it carries two instruments to detect energetic neutral atoms that are formed during the collision of charged particles from the solar wind with cold, neutral particles from the interstellar medium. These neutral atoms are created through a process known as charge exchange, where charged particles transfer their energy to neutral atoms, causing them to become excited and emit a new neutral atom. The IBEX spacecraft was manufactured by Orbital Sciences Corporation, now Northrop Grumman, and was launched on a Pegasus rocket on October 19, 2008. The spacecraft was designed to have a nominal mission life of 2 years, but it has since been extended several times and is still operational as of 2023. The total cost of the IBEX mission, including spacecraft development, launch, and operations, was approximately $169 million. This cost is relatively low compared to other NASA missions, but it reflects the relatively small size and scope of the IBEX mission. The spacecraft itself is relatively small, weighing only 110 kilograms or 240 pounds and measuring 1.2 meters or 4 feet in diameter and 1.7 meters or 5.5 feet in height. It carries a suite of scientific instruments, including 2 sensors that detect energetic neutral atoms and a third sensor that measures the solar wind. The IBEX spacecraft was designed to operate in a highly elliptical orbit around the Earth, with a perigee of approximately 48,000 kilometers and an apogee of approximately 322,000 kilometers. This orbit allows the spacecraft to study the distribution of neutral atoms in the heliosphere from a vantage point outside the Earth's magnetosphere. The IBEX mission has been instrumental in advancing our understanding of the region of space surrounding our solar system. By mapping the distribution of these energetic neutral atoms, the spacecraft has allowed astronomers to better understand the dynamics of the heliosphere, which is the region of space dominated by the solar wind. This information is critical for understanding the broader context in which the solar system exists and the dynamics of the interstellar medium. The IBEX spacecraft operates in a highly elliptical orbit around the Earth, with its closest approach being only about 12,500 miles from the planet. This orbit allows the spacecraft to maintain a consistent view of the region of space being studied. The mission has already produced significant scientific results, including the first direct measurements of the interstellar wind, which provides important information about the nature of the interstellar medium. Additionally, the IBEX data has helped to refine models of the heliosphere and provided valuable insights into the interactions between our solar system and the interstellar medium. As we just mentioned, the purpose of the Interstellar Boundary Explorer spacecraft was to study the boundary between the solar system and interstellar space, specifically the region where the solar wind collides with the interstellar medium. This region is known as the heliosphere, which is the region of space dominated by the solar wind. The IBX spacecraft was equipped with instruments to detect energetic neutral atoms that are formed during the collision of charged particles from the solar wind with cold, neutral particles from the interstellar medium. These neutral atoms are created through a process known as charge exchange, and by mapping their distribution, the spacecraft has allowed astronomers to better understand the dynamics of the heliosphere and the interactions between our solar system and the interstellar medium. The IBX mission is important because it provides valuable information about the boundary region of the solar system and interstellar space, which is an area that has not been well studied in the past. The information provided by the IBX data is critical for understanding the broader context in which the solar system exists and the dynamics of the interstellar medium. The IBX spacecraft has already produced significant scientific results, including the first direct measurements of the interstellar wind, which provides important information about the nature of the interstellar medium. Additionally, the IBX data has helped to refine models of the heliosphere and provided valuable insights into the interactions between our solar system and the interstellar medium. Neutral atoms are atoms that have no net charge because they have an equal number of protons and electrons. In contrast, an ion is an atom or molecule that has a net electric charge due to the loss or gain of one or more electrons. Neutral atoms can be formed through a process called charge exchange. Charge exchange occurs when an ion collides with a neutral atom or molecule, and one or more electrons from the neutral particle are transferred to the ion. As a result, the ion becomes neutral, and the neutral particle becomes an ion. The net effect of this process is the exchange of a charged particle for a neutral particle. In the case of the IBX spacecraft, neutral atoms are formed through the collision of charged particles from the solar wind with cold, neutral particles from the interstellar medium. The solar wind is a stream of charged particles, mostly protons and electrons, that are constantly blowing out from the sun, while the interstellar medium is the gas and dust that fills the space between stars. When the solar wind particles collide with the interstellar medium, some of the charged particles will undergo charge exchange with the neutral atoms and molecules in the interstellar medium. These collisions produce neutral atoms that are then detected by the IBX spacecraft. By mapping the distribution of these neutral atoms, the IBX spacecraft can provide information about the dynamics of the heliosphere, which is the region of space dominated by the solar wind, and the interactions between the solar wind and the interstellar medium. This information is critical for understanding the broader context in which the solar system exists and the dynamics of the interstellar medium. The IBX spacecraft has provided valuable insights into the dynamics of the heliosphere, which is the region of space dominated by the solar wind. By studying the distribution of neutral atoms, the IBX mission has been able to map the boundaries of the solar system and the heliosphere. This information has been critical for understanding the broader context in which the solar system exists and the dynamics of the interstellar medium. One of the key findings of the IBX mission has been the discovery of a previously unknown boundary at the edge of the solar system. This boundary, known as the IBX ribbon, is a narrow band of intense neutral atom emissions that stretches across the sky. The ribbon is believed to be the result of the interaction between the solar wind and the interstellar medium. The IBX mission has also provided insights into the structure and dynamics of the heliosheath, which is the region of space between the termination shock, the boundary where the solar wind slows down as it interacts with the interstellar medium, and the heliopause, the boundary where the solar wind is stopped by the interstellar medium. By studying the distribution of neutral atoms in this region, scientists have been able to better understand the complex interactions between the solar wind and the interstellar medium. In addition, the IBX mission has provided information about the interstellar magnetic field, which is critical for understanding the dynamics of the interstellar medium. By studying the distribution of neutral atoms in the heliosphere, scientists have been able to make indirect measurements of the interstellar magnetic field. So, there you have it. NASA's solution to fixing the $169 million IBX spacecraft was as simple as turning it off and back on again. But don't be fooled by the simplicity of this solution. The data collected by the IBX mission has provided valuable insight into the dynamics of the solar system and the interstellar medium, and has helped scientists to better understand our place in the universe. Like and subscribe if you enjoyed this video and join us again next time. Thanks for watching.